Hi everyone, welcome to the last last lecture of this course, other than the summary that I'll do in the end. In this video, we are going to use everything we developed about finite free probability and prove the existence of one-sided Ramanujan graphs of every degree and every event size. Okay, so let's get to it. The main theorem that we are going to prove is a theorem by MSS. And it says that for every degree, it also holds for 2, but it's not interesting. So for every degree larger or equal than 3, and every even n, there exists a deregular undirected graph on n vertices. Now, this graph can potentially have parallel edges. Okay, so it's in a sense it's sometimes it's considered illegal, and sometimes it's a problem. But that's what it is. And that graph. For that graph, we know how to bound its second largest eigenvalue. Of course, the first eigenvalue is just d because the graph is deregular. And what we'll show is that the second largest eigenvalue is bounded by 2 square root of d minus 1, the magical number. And we know that by the Alon-Bopana bound, we can't do better than that asymptotically as n goes. So why we call this one-sided Ramanujan? Well, we don't bound here lambda n, right? Only lambda 2 from above. In some applications, that's enough. In other applications, when you want like a full-fledged spectral expander, you need also to bound lambda n from below. Now, for bipartite graphs, by the way, you can show that the spectrum is symmetric around 0. So a bound on lambda 2 gives you a bound on lambda n. But you need to work a little bit harder in order to prove the existence of bipartite Ramanujan graphs. And this is something that we'll cover in the seminar. You need to consider not the additive convolution that we had, but rather the kind of a variant of that. And anyhow, so this is the theorem that will prove it's slightly, I don't know if it's stronger, but a variant of this result that also gives you what's called bipartite Ramanujan graphs of every degree and every even size. Okay, so that's the theorem that we are going to prove, and that's a remarkable result, right? I mean, so I think historically people weren't sure that you can actually do that for every degree, because previous constructions, as we talked about, I think at the beginning of the lecture, the previous constructions from the LPS and Margulis, it kind of heavily used group theory, and you needed the degree to have some relation to a prime. It must have been a prime power -1 or so forth. So it wasn't clear if this structure is required in order to construct Ramanujan graphs or not. And well, this theorem tells you that it's probably not. I mean, it could be the case that potentially, but it's going to be weird if that's the case, that the graph that you obtain from this theorem happens to coincide with the graph that you get from the group theoretic results. I mean, we don't know if that's not the case, but for these which are not prime powers, this gives you something that was not known before, and also was not known for every size. So there was a previous work of MSS that handled every degree but not every size, and this handles every degree and every size. And that previous result will also be covered by the seminar part, hopefully, if one of you will take the paper. Okay. So let's move on and prove the theorem. So the idea is to start like in a probabilistic method mindset by looking at the distribution of the irregular graphs, and somehow proving that in expectation something good happens, and therefore there is a point in the sample space that is as good. So let's try to formalize that. And again, this entire video is about kind of collecting all the results that we had and putting them in place. There is nothing very difficult here going on. So let's consider the sample space in which we sample d permutations independently. So P1 up to PD are actually the matrices corresponding to the sampled permutations. So these are randomly permutation metrics that have been sampled independently. These are n by n matrices. Let's look at M, which is the adjacency matrix of some fixed matching. 1 is matched to 2, 3 is matched to 4, and so forth up to the last couple. That's why we need n to be even. And so this graph, if you think about it, is the union also allowing for multiple edges, but it's the union of, you take the perfect matching, M, you permute it according to P1, so that gives you another perfect matching, and that's this one. And then you do the same for all of the permutations that you have, and you take the union, again, parallel edges may appear. So I think of this as a distribution over graphs. It's really over the adjacency matrix of the graphs, but we will, think of them as equal. And so what we want to prove is that there exists a point in this sample space, namely a choice for P1 to PD. So let's denote it, emphasizing that that's a particular choice by P1 hat, PD hat, for which lambda 2 of this graph or operator is bounded by 2 square root of the minus 1. That's what we want to prove. Right? That there exists a point in the sample space. There are D permutations such that if you fixed permutations, such that if you permute your whatever perfect matching, it doesn't matter, that you started with according to them and take the union, you'll get the best mount possible. So we are in, as I said, probabilistic method mindset, and so we would want to reduce the problem of proving the existence of such d-tuple to somehow showing that in expectation everything works well, and from that it deduce something about one point in the sample space. And for that, let's first result what's the result that we proved for interlacing. So this is theorem 1 in the interlacing unit, which was just yesterday. So let's say that you have two n by n real matrices A and B, and if you recall, we require this fact that the all ones vector is an eigenvector of both A and B with possibly different eigenvalues, little a and little b. Then what we proved is kind of a probabilistic method argument. We proved that there exists a permutation matrix such that if you look at the characteristic polynomial of A plus B when B is conjugated using that permutation matrix, and you kind of ignore the obvious A plus B root of that polynomial, then the max root, so the remaining root, you can actually show the max root of this thing is actually smaller than A plus B or equal to it, but it doesn't really matter. So the max root of that polynomial is bounded by what happens in expectation. Namely, here you don't fix P, you go over on the right-hand side. You go over all possible P in Sn, like you sample P in Sn according to the uniform distribution. And you, again, ignore the x minus A plus B factor, which is common to all of the polynomials there, and you look at the max root there. So that max root, so let's call it as we did before. The max root of the non-trivial max root of the expected characteristic polynomial bounds the max root of some polynomial that participate in the expectation. So that's what we proved. And here we are going to need a slight variant of that, a generalization for the sum of D matrices, but it's kind of the same thing. Like if you think about it, the way we proved interlacing was to construct this tree where you slowly kind of build up your this expectation over uniform permutations over Sn. At the leaves you had like the fixed permutations, or there were many leaves, but fixed permutations appear on the leaf, and at the root you had the uniform distribution. And now if you have several of these, it requires a little bit of work, but if you have several permutations, P1 up to PD, then you work your way one permutation at a time. So at the leaves of everything, you have all permutation fixed, and then you have these trees that slowly but surely make sure that, say, the last permutation at the root of this subtree is uniform, whereas the remaining permutations are fixed. And then from there, at the second level, you go on and start to randomize the second to last permutation all the way through the root, which will have all permutations being random and uniform. So, this is exactly one of these things you don't want to do in a course because it's not insightful and it's just the same thing. So you can look at the papers. Anyhow, so let's kind of connect that theorem in its generalized version to the matrices, the permutations with our scenario. So in our scenario, right, the thing that we are looking at, and this is from the previous slide, you want to prove that the second largest eigenvalue of this operator is bounded by whatever 2 to the square root minus 1, and lambda 2 of that operator is the max root of, right, the characteristic polynomial corresponding to this matrix, divided by the obvious x minus d factor. Right, it's x minus d because this is m here in which was a here has a 1 as an eigenvector with eigenvalue 1, and you sum d of those. So the eigenvalue corresponding to eigenvector 1 of this operator, which is indeed an eigenvector of this operator, is d. So you divide by x minus d, and you are looking at the max root of this thing. That's the same as lambda 2, just to connect it to this theorem. Okay. So what this theorem tells us is that if you want to bound this number that we want to bound, it's enough to consider the expected characteristic polynomial. So it's enough to bound the non-trivial max root, or the second largest max root, because it's going to be the second largest. I'm not using that, I'm just lambda 2, let's denote it, of the expected characteristic polynomial. So see here you have the expectation, whereas before you didn't have one expectation. That's potentially an easier problem. Like if you believe the mindset of the probabilistic method should apply somewhere here, then that should be an easier problem. Because you don't need to argue about structure, you need to just hope that randomness is sufficient for your problem in some sense. Good, and also, right, if you remember, up until like the last video, we didn't even know that this is real-rooted, but now we know that this is a real-rooted polynomial, so it makes sense to talk about the second largest root of that polynomial. Good, so that's our goal. Our goal now is to bound lambda 2 of the expected characteristic polynomial with respect to permutations. So interlacing allows that to do that. And quadrature will enable us to make this problem and kind of translate it either if you want to R, but we're kind of going to skip immediately to saying that it will enable us to skip to understanding the free finite additive convolution of certain polynomials in order to understand this expectation. So let me remind you what the quadrature result was, and then we can go back and see how it's related in our setting. So this is just like I copy pasted from the relevant unit. So if you have two symmetric matrices A and B as before, right? So the eigenvalue of one is an eigenvector of A and B, and with corresponding eigenvalues A and B, little a and little b. And let's say that you kind of factor out the obvious x minus a and x minus b part of the characteristic polynomials left with p of x and q of x. Then quadrature told you that this expected characteristic polynomial is actually, okay, so you have this obvious factor, but the remaining part, the interesting part, is obtained by taking the d minus first free finite additive convolution of p and q. Right, and again, we can easily, that's actually a black box thing, you can easily reduce that to, you don't have to redo it to the setting where you have d summits, because you can just peel out one at a time. And I don't know if I ever mentioned that, but this operation is associative. That's one way of proving that actually. It's also obvious from the way from our first definition, also from our second definition. No, our first definition is easier to see because sum of matrices is associative. Anyhow, so that's the quadrature. And in our setting, it tells us that our new problem, which was to understand the expected characteristic polynomial in terms of permutation matrices, well, that particular polynomial, not just lambda 2, but that particular polynomial is, in fact, x minus d. That corresponds to this thing, because we have x minus 1, like 1 appearing d times this thing. So it's, you take the n minus first convolution, let me not say finite free and so forth, convolution of a certain polynomial, like the p here, let's call it m, and we'll talk about it in a second, with itself d times, right? So that's equality of polynomials. And we know that m of x, right, looking here, is the characteristic polynomial of the matrix M divided by x minus 1, because x minus 1 is the trivial factor that you should factor out from the polynomial. That's the eigenvalue corresponding. That's the eigenvalue corresponding to eigenvector 1. So really m of x is this polynomial, because the characteristic polynomial of a perfect matching is just this thing. Right, it's x minus 1 to the n over 2 times x plus 1 to the n over 2, just because the eigenvalues of a perfect matching are 1 and minus 1 with equal multiplicity. So when you divide by x minus 1, you get this kind of annoying minus 1 here. Okay, so if you want to understand this polynomial, and you do because of the interlacing, then you just need to understand that polynomial. And understanding that polynomial essentially means that, well, you need to understand m of x, but that's a very simple polynomial, and how the additive finite free convolution behaves. And that's for that we developed the R transform field. Right, so to recap, we need to understand this polynomial and actually the max root of that polynomial, because d is going to be the largest root of the previous polynomial, and so the max root of that will be the second largest max root of the thing that we want. You can actually easily show that for a d-regular graph, the largest eigenvalue is going to be d. And you can, it has nothing to do with free probability. It's basic spectral graph theory. You can do it as an exercise. So, okay, but how do we bound the max root of any polynomial? Like, max root is a kind of a difficult function, but well, the point is that the K transform always give you a bound on the max root of a polynomial, right? I mean, in free probability, the K transform was kind of a way to go back to the Cauchy transform, its inverse, and from there using the Stieltjes inversion formula to the measure itself. In finite free probability, the way we are using the K transform, as we said, is to bound the support, at least from one side, like to bound the support. So in this case, bound the largest eigenvalue or largest root of whatever polynomial that you're looking at. And if you remember particularly what you knew is that the max root of any polynomial, this is just a shorthand for this polynomial, but it works for every polynomial, real-rooted polynomial, of course, is bounded by the K transform applied at any point which is positive. And it's actually a strong inequality, by the way, it's a strict inequality. So technically, you get a strict inequality in the theorem and so on, but asymptotically, it doesn't really matter. Right, so this, some people think of it as, in a sense, like kind of a softmax thingy. I mean, there is a way to interpret the K transform as a softmax in a way, but I didn't present that in that from that perspective, so I don't want to go there. But you can kind of see it. I mean, the K transform always bounds from above the max root, so in some sense, it's a softmax or something. So if you want to bound the max root of whatever polynomial you want to bound, you just need to understand its K transform. So you want to understand the K transform of this polynomial. And once you do that, you are going to choose a W which minimizes the right-hand side, so to get you the best bound that you can. And what's going to happen is that we are going to understand this K transform, and we're going to look at it, and we're going to see that some specific W gives you a value here, which is 2 square root of d minus 1. Okay, that's what's going to happen in the next like 4 slides. And that would conclude the proof if you collect everything we did so far. And actually, we did all of these computations before, because if you remember, it was for a different kind of reason. But if you remember, we already saw the x minus 1, x plus 1, or not x minus 1, x plus 1, but we already saw a distribution which with probability half it's minus 1, probability half it's plus 1. And then we did take its diff convolution, additive convolution, but not finite, diff additive convolution, and that gave us the Kesten-McKay distribution. And it's going to be the same computation completely, because when we are going now to write the Cauchy transform, it's going to completely kind of ignore these n over 2s. So whatever computation we did actually holds here. And so the computation we did there was to understand, to get back the measure, the Kesten-McKay distribution. Here we're just using it in order to bound the second largest eigenvalue, or the max root of this polynomial, convoluted with itself, d times. But I'm just going to redo it so that, like, not do the entire calculations, but just revisit all the steps so that you won't have to go back and forth. You should just understand that we did it for a different reason. Okay, so now let me cheat a little bit because it's valid and it's easier. Let me, instead of considering this annoying polynomial with minus 1 here, mx, let me just do everything for the characteristic polynomial of the perfect matching. So it's just more symmetric, and it kind of removes the n appearing everywhere. And it's actually fine. I mean, a bound that you get for this polynomial implies a bound for the previous polynomial. So I'll leave it to you as an exercise if you want. But well, I'm just going to work with this polynomial, and you just have to look at the first couple of steps and see that this is actually a more restrictive inequality. So whatever we do here holds for the annoying polynomials. Okay, so the Cauchy transform. So I want to talk about the K transform of this polynomial convoluted with itself d times. So we should start with before the convolution, right? Just just considering the Cauchy transform of one perfect matching, and then through the R transform, we can easily understand what happened in a convolution. So the Cauchy transform of one perfect matching, which technically I should write G of the characteristic polynomial of M, but let's just write G of M. Also, there is this annoying thing that if you write x of M here, then you have like two x's that are doing different things. So I'm just going to write M. But even if I'm not going to write M, I'm going to write 3 of M without mentioning the particular like variable, which doesn't really matter, of course, in the characteristic polynomial. Anyhow, so the Cauchy transform of M is this thing, right? It's you can do it in several different ways, but one way is to take the divide by n and then look at the derivative of the characteristic polynomial over itself, or you can just look at it and see that you have, with probability n over 2, you have x minus 1, with probability n over 2, you have x plus 1 in the denominator. Anyhow, this gives you that, and that's what I said about n doesn't appear in here. So if it doesn't appear here, then the computation that we did in the free probability part is actually valid here as well. But never mind that. And now we want to invert it, because we want to compute the K transform as a step to compute the R transform. And from the R transform, you can go to the R transform of the convolution and get back the K transform. So we want to invert that under a composition, of course. So so that you can compute Km of W. And let's call it little k just to save notation. So if you want to invert that, what you really want to do is to solve, and I think of k as its input variable, and I'm going to denote it as W. So what you want to solve for k, this equation in terms of W, k, which is k of W, right? I'm putting W here and I'm replacing everything here by k. So if you play with it a little bit, you get this inequality. And or before moving on, this is just a picture of the Cauchy transform, so that we'll have a sense of how it looks like. Okay. Anyhow, going back to the K transform, we want to solve this inequality, and you can just solve it again using the quadratic equation, which holds fine in our setting. And you get two solutions, and actually draw the two solutions once so that you will see them. You need to choose the right one. It's going to be the one with the plus. And these are the two solutions. You have this one, the red one, and the blue one. And both of them are actually inverses, but on different regimes. And we want the max inverse, the one that looks like 1 over z also, or 1 over w, or something like that. The one that makes g looks like 1 over w. So, right, so if you look at the Cauchy transform, you see you want to invert this thing. You don't want to invert that thing. You can invert the different functions when restricted to the branches because they are one-to-one on those domains, but you want to kind of invert that part and not that part, and this is exactly what, and definitely not that part, by the way, and this is what this gives you, right? So the Cauchy transform is this thing, that's the plus, the minus will invert exactly the thing that we saw before, and this technically is kind of connected with that, but we don't care about W smaller than 0. Good, so we found the Cauchy transform, and from here we compute the R transform. So right, so the R transform is just the Cauchy minus 1 over W, and it looks like that. Now, when we did finite free probability, here we had a theorem that tells us that it's a very strong theorem that tells us that the R transform of the diff additive convolution, sorry, of adding M with itself D times according to the convolution equals D times the R transform of the individual R transform the individual distribution, the marginal. Here we only have an inequality in the finite R transform theorem. And what I mean only, it's like a very strong theorem, right? Actually, also, I think here you have a strict inequality, because if you remember, there was an equality if and only if the one or two of the two measures were constant, but none of them is constant. So you have like double strict inequalities in the proofs, but it doesn't matter to anyone. So anyhow, at least we have a bound, right? Which was very hard to prove on the R transform of the M convolution with itself D times. Just multiplying this by D, so you get this expression. And so going back to the K transform of the distribution that we care about, because that's what will enable us to bound the max root, just by adding 1 plus W, we know the K transform is just adding to that 1 plus W is bounded from above, because we inherit this bound by this expression, which was the exact same expression that we got when we did free probability, but with an equality. I think I just open it up and show you. It's not a... Right, you see, so we got this thing from the previous, some previous unit, but then we continued on to compute the G transform. It was some point of calculation. And then from that, using Stilzis, we found the distribution, which is Keston-McKay. Here we only have a bound, so there was no reason to try and invert it, because it won't give you any information. Just a bound, it's not a characterization of this, it's not the same thing. So, but it's the same thing. The only difference is that here I put the D minus 2 in the brackets, that's it. Good. And this is the finite R transform that I used. I should have maybe mentioned that, but that you remember that it's a very simple theorem. And also it generalizes to sum of any number of polynomials, or like sum, additive convolution of any number of polynomials, because it doesn't really matter. Also, this D is a bit confusing, because in our case, D is the number of summands, and this should be like n minus 1 or something in this case. But it doesn't matter as well. Anyhow, we bounded the K transform of the polynomial that we care about, or maybe a slight variant of it, because I was too lazy to handle the -1, which is fine. So what you want to do is to bound. I mean, so let me get back to it. So we have a bound on the K transform as a function of W, and for every W larger than 0, that gives you a bound on the max root of that polynomial, which in turn gives you the bound that you want on lambda 2. So what's left to do is to choose the best W. Every W works. It's larger than 0. So if you remember, right? So it's kind of a trade-off. So if you choose W that's smaller, that is larger and larger, you get closer to the max root. But here, because of the way the bound is okay. No, wait. So let's look at BW, that's the bound that we had on the K transform. So it actually looks like that if you want to see a picture. We already saw this picture because it's not a bound when in the free setting, the infinite free setting, it's just the K transform. So we actually had a nice picture of that with ABC, and then we looked at the ABC and the Cauchy transform. But now it's just for the sense now it's just for the purpose of finding a bound. So this is the K transform, and want to find is this point, because you want to minimize this bound on the K transform, which is a bound on the max root. So you want to find this point. So there is a little bit of trick that you can do, but let's just do it in the obvious way. So you can differentiate, and this is the derivative of B. And just equating to 0, you get that the W that minimize that is square root of D minus 1, which start looks good, divided by D minus 2. And if you plug this back into B, it's trivial, just do the calculation, you get the desired 2 square root of D minus 1. Okay, so that's essentially it. I mean, just to recap, we had this problem where we wanted to prove the existence of depermutation matrices that would induce the regular Ramanujan graph, and using interlacing, we reduce the problem to a problem of bounding the expected characteristic polynomial, but the expectation is with respect to permutations, and using quadrature, that problem was the same. That polynomial is the same as a polynomial which involves the finite free additive convolution, which hides Har inside there, but you can think of it as part of the proof if you want, and not part of the result. And also we saw that Har is not the only distribution that is suitable here, but any minor orthogonal distribution, which Har is, will give you that. So it's in a sense, it's an abstraction. So anyhow, to understand the finite additive free convolution, we had the finite R transform, which I think was the most difficult theorem in the finite free probability things that we proved so far. And the thing that we should have in mind is that we understand or think of the K transform as a way of bounding the support or the max root rather than as a one step before getting the Cauchy transform, and hence the entire distribution, because here we only have a bound. Right, so that's it. You just prove the existence of Ramanujan graph of every degree and every even size. That's just a remarkable result.